as our speaker. As some of you might have gathered, a few of us have been working with Umair for the last 2 or 3 years. Umair is an assistant professor of geophysics at King Fahd University of Petroleum and Minerals in Dhahran, which, for those of you who know, there's a fence sort of dividing the university from the Aramco research base there. So he's very close to some of our colleagues, physically, some of our former colleagues who are in Saudi Arabia working at Aramco. His interests are broadly in the area of computational geosciences, and recently he's been working on looking at smart algorithms for enhanced decision-making in subsurface energy systems. He graduated from KAUST, King Abdullah University of Science and Technology, with a PhD in 2015. He was also then a postdoctoral fellow at Princeton. And one thing I didn't realize until he gave a post-convention workshop at SEG a couple years ago is that he was also a fellow at Princeton for writing and science, and he's given seminars since then, or classes on how to write. And I think one of the comments he made to me when I asked him about this, which I thought was very important or significant, was he said that when you're writing, you should always have empathy with your reader. And I think it's something that a lot of us could keep in mind as we write. And not having taken his class, that was an important lesson that I took away from just talking to him. But anyway, today he's going to talk to us about some work he's doing on using machine learning methods to solve problems in physics. So Umair, it's yours.
Thanks a lot, Mike, for the nice introduction. Thank you so much for your kind words. I just want to confirm if you're able to view my screen here.
Yes.
Okay. All right. Thank you, everyone, for coming. And it's a matter of great honor and pleasure to be speaking to you all. At least, I couldn't be at MIT, but virtually we could do this. And that's excellent. So today I'll be talking about travel time modeling and inversion using physics-informed neural networks. And I'll also be touching upon a little bit of the other things that I'm doing first, and then move on to talking about the main topic for today. Okay, so just to get things going, I think it's a very important time that we're living here right now in this world, because we don't often get to see an industrial revolution happening in front of our eyes. And the one that we are seeing unfolding in front of us is what is being dubbed as the fourth industrial revolution. And therefore, the thing that separates the fourth industrial revolution from the third is the fact that how fast the technology is moving and how much it's merging with our lives, right? So think of technologies like Face ID recognition, self-driving cars, voice-activated personal digital assistants, healthcare sensors. All of these things are, getting into our lives and becoming part of our lives. Now you can even have a 3D printed, bone for surgery and stuff. So AI or artificial intelligence is one of the biggest enablers of the fourth industrial revolution. But like any other revolution, I think a lot of us are also skeptic about it. And this is not new because, while we're thinking about AI and what are the good and bad of AI, similarly, our ancestors, maybe 100 years ago, were talking about electrification of the society. And they were concerned that electricity would take our jobs, might kill people, and so on and so forth. But now we can feel that the electrification of society, elevated the quality of life, and we are better off, than we were back in those days, right? And therefore, I strongly believe that AI or deep learning or machine learning will also create new opportunities and in terms of advancing the society. Now, if you're new to AI or machine learning or deep learning, and you may have heard talks and people interchangeably use these terms, it sometimes gets very confusing that what is the difference between these three terms. So essentially, this talk is mostly about deep learning, which is a subset of machine learning in which artificial neural networks adapt and learn to vast amount of data, right? So typically, you need a lot of data to train these deep learning models. And just to make sure everybody is on the same page, a neural network is composed of multiple neurons connected together, and each neuron is a computational unit that takes weighted sum of its inputs, applies passes it through a nonlinear function, and passes it to the next neuron in the sequence, or as to the output layer, for example. And when you stack these neurons together, it gives the network this amazing power of learning nonlinear relationships between your input and output, right? So what you see here on the screen is one of the neural networks that was used in the 1980s with a single hidden layer, because at that time, we could only train this kind of shallow neural networks. Now, in the recent past, neural networks have impacted many domains of science and engineering thanks to deep learning, which means you can now stack these multiple layers and kind of make your network learn highly nonlinear relationships between your input and output. So now you can approximate a lot more complicated functions than you could in the days of 1980s or 1990s, those days. So for example, if you are trying to train a neural network for image detection, you feed you prepare a lot of training data where you have labels. So for example, you have you're trying to classify images of US presidents, and you will gather a lot of those images and train your neural network, and there will be a tug of war mechanism between these weights. And once these connections, which contains the weights, actually they get trained, eventually it will start to recognize unseen data and kind of give you predictions for that. So the power that deep neural networks have is because of these different layers that learns highly abstract features. So as you can see here in the beginning, it's just pixels in an image, and then these pixels are combined in the first layer to form different parts of shapes, such as part of a lip, part of a nose, and so on and so forth. And then in the next layer, they're even more combined to identify, combinations of edges like this nose here or the eye, and so on. And then you go on further, and it kind of builds on the things that's identified before, and eventually you will get these kind of images where it could learn to classify different objects. And if you want to think of why deep learning or this layer of networks, the power that it has, is one way to think of it is, imagine you have a piece of paper and you have a lot of data points marked in there, which you need to separate. You need to draw a very complicated boundary. Now, deep learning allows you the power to fold that page such that it makes life easy to draw that decision boundary and separate those classes of data. So the talk today will be about deep learning in general, but I'd like to start by talking about a few of the research topics that I'm interested in. Maybe you will also feel interested, and feel free to talk and communicate about this, and we can discuss this. So this will be pretty fast, just a quick glimpse of the different things I'm working on. And this is a work jointly done with Mike Feller, and there is an interesting story about it. So what we are trying to do here is to detect low magnitude earthquakes, so microseismic events that we are trying to identify. And one of the biggest challenge is, in the presence of strong coherent noise coming from the surface. So if you have a sensor somewhere close to the surface, and there is some I don't know, construction going on, some other sources of noise, it's pretty hard to identify these low magnitude earthquakes coming from the subsurface. Most of the literature on, or pretty much all the literature we've seen, what they do when they use deep learning is they look at a single sensor. Now, when you're looking at a single sensor, it's pretty hard to know whether the energy is arriving from the surface or the subsurface. So this was something that we were discussing with Mike, and Mike was telling us how he manages to go back and verify which of these are true events and which of them are not true events. And therefore, we apply our data on the Groningen data, where we kind of apply this strategy that Mike was doing visually through a convolutional neural network. So what we do is we have this borehole sensor network, and we only look at these 4 velocity sensors. And if there is energy coming from the subsurface, it will arrive first at the deepest sensor. And the opposite is the case for when energy is coming from the surface. And therefore, you would have a move out pattern here. For example, in case of a true event, it arrives first at the bottom sensor, and then it moves up. While the opposite is the case for noise coming from the subsurface. And therefore, convolutional neural networks are really smart at identifying these visual changes, and therefore this is what we did, try to, copy the idea that Mike does visually through a convolutional neural network using data from Groningen, which of course you guys would know has a lot of problem with induced seismicity. On the same theme of microseismics, one of the other problem is, that oftentimes you have to stop operations because there are some, let's say, events that go beyond certain threshold, and therefore people employ a traffic light system, and traffic light system requires quick identification of location. So this is what we did in this work, where we train a deep neural network to look at the travel time peaks at the stations and give us a location coordinate. So neural networks are really good at being trained offline, and then once they are trained, you bring them online and they perform the task instantaneously. So this is a method in which we pick locations on this data from Woodford Gas Shale Reservoir in Oklahoma, and we compare its performance with the maximum likelihood method, and we get really high accuracy in near real time. The third thing, and if there are people here in the audience that are interested in rock physics, what we do here is, in rock physics, you're trying to ascertain properties delineated from CT data, for example, and it is highly correlated with the quality of the CT image. So what we do here is we train a convolutional neural network to look at this poor quality image, which is a low exposure image. So if you scan for, let's say, 0.5 seconds, you get something like this. Whereas if you scan longer, you start to see things more clearly. But once we gather this kind of data for some samples, we could train a convolutional neural network from now on to take this kind of thing as input and produce something which you see on the right, which is highly, let's say, denoised. And this helps us achieve, better temporal resolution, which is important for studying dynamic phenomena like flooding. Another thing, if there are geologists in the audience, one thing that geologists do all the time is they look at samples, visually, rock samples visually, and they do a lot of analysis visually, which is tailor-made for computer vision tasks. And all of these problems have been solved in the field of computer vision. So you're trying to bring that knowledge into the field of geology. And if you can look at these images and ascertain different, and use it for different classification tasks like bioturbation analysis, facies classification, predicting porosity, etc., and allows fast, accurate, and consistent classifications. And what happens with geologists is that their performance depends on the time of the day. So if a geologist is kind of doing this analysis in the morning, that performance would be different than maybe at 4 p.m. And whereas performance of this convolutional neural network is independent of this factor, right? And you can get real-time evaluations, right? So you can take your algorithm on your phone, and maybe when you're in field, you could also do this kind of analysis. Now, all of these things that I've just talked about, they're purely data science methods, right? So they rely on data and they don't involve any physics. And there is a big trouble with ignoring all the physical laws that people have developed over centuries, basically, right? And just relying on data now. This is probably not the best way to approach scientific problems. And one case that is worth mentioning here is the failure of what was called the Google flu trends. So this was a system that was designed to predict the onset of flu just based on Google search queries. And it performed well in the beginning during the training phase, but soon it started overestimating, and it by a great percentage, and eventually it had to be taken down because it was not performing satisfactorily. And if you look online, you will find a lot of such examples. And one such example is maybe what I read maybe a few months ago was about this soccer game where the camera was controlled by an AI algorithm. And the camera kept switching between the ball. So it was supposed to track the ball, but it kept switching between the ball and the bald referee, because it thought this looks something like a ball, right? And these things may happen, and while we may laugh about these things, right, they can be fatal and catastrophic when it comes to, maybe if you think about self-driving, a car crashes into another vehicle or a person just because it wrongly recognizes these things, because it's purely data-driven, right? or AI medical diagnosis system misidentifying or misdiagnosing a disease. Those things can be really catastrophic. So this brings me to the topic for today, which is about how we can involve physics into our machine learning workflows, or how we can use, let's say, physics-based machine learning models. So the two examples I'll talk about are about travel time modeling and travel time tomography. So one is about forward modeling, and the other is about inversion. So let's get started with the first part, which is on travel time modeling. And before I go on, I'll just give you a quick background of the eikonal solvers and their history, because eikonal solver is what we eikonal equation is what we use to solve for the travel times. And there's a rich history, and there's been a lot of work done in the field of eikonal solvers. It started in 1980s with John Vidale's algorithm called the expanding box method, and prior to that, it was mostly ray tracing, and therefore, if you could solve this system now by directly solving the eikonal equation. And then people came along and they kind of, let's say, extended this method, for example, to include an anisotropy and extending into 3D, improving the accuracy using high order method, etc. Right? However, soon after Vidal's work, another method was proposed called the expanding wavefront scheme, because of the problem or instability issue of the expanding box method with diving waves. And then people came along and they kind of extended the work done in the domain of expanding wavefront scheme by doing different things like finding out travel times for maximum energy travel times, and adding an isotropy and a hybrid method between expanding box and expanding wavefront scheme, called the group marching method, and so on and so forth. But one thing that got popular in the 1990s was the fast marching method, because of many properties and its stability and speed. And it got really famous in mid 90s and to late 90s. And then a lot of people came along and they extended the method to include an isotropy in the medium, improve the accuracy, and add parallelization to compute solutions faster. And it enjoyed a lot of success, and still one of the go-to algorithms to solve the eikonal equation. But in mid 2000 came the fast sweeping method, which is perhaps most widely used method in many different domains wherever eikonal equation is used. And since the fast sweeping method was introduced by Hongkai Zhao, people came along and they again, similar to the past practice, they developed things for improving the accuracy of this method. And I spent a lot of time during my PhD working on the fast sweeping method, incorporating an isotropy into the method. And also people came along and tried to improve, let's say, the computational aspect of it. Now we're talking about how we can use neural networks to solve the same old problem, right? And we'll see in a while why is it worth doing so, and what are the advantages, right? But one thing is for sure that we have made a lot of progress during the past 30 years in the field of eikonal solvers, and we know a lot about them in terms of their advantages and limitations. So let's see if a neural network-based eikonal solver could address some of the inherent challenges or outstanding challenges that we face. Now, the idea to use neural network to solve PDEs has been around since the 90s, actually. However, recently, it got really popular through this paper of Mazia Raisi, who developed the PINN framework to solve PDEs. And PINN is short for physics-informed neural networks. Now, the main difference was the possibility to, let's say, compute derivatives of output with respect to input through automatic differentiation. That made a huge difference. Back in the days, people had to rely on I think, hand calculated derivatives and so on. But now you can have, which can be really tedious. And now you can have smart, or let's say, very fast algorithms that could do that for you. And I'll talk about that in a bit. So in this work, what I'm going to talk about, we develop a PINN-based method to solve the eikonal equation. So we look at the eikonal equation and the requirements that it has, and try to adapt the PINN framework to solve the eikonal equation in a holistic manner. And what do I mean by a holistic manner? You saw that there were little bubbles coming out of that main algorithm, but now you're trying to solve everything in one go, right? Can we address all of those challenges here with one algorithm without having to extend the method and spend a lot of research energy on those things? One good thing about the proposed method is that it could use information gained from one solution to the next, unlike conventional methods. If you solve a problem for one domain, let's say for a given source receiver configuration for a given velocity model, when you have a new velocity model, you have to repeat the same amount of computational effort, right? Whereas now with neural networks, we have the ability to use that information that we have gained by solving that problem initially. All right, so first thing we need to have is the eikonal equation, which is a nonlinear first order hyperbolic partial differential equation of the form here shown, which tells us basically the gradient of the arrival time surfaces is inversely proportional to the velocity. So if you have, let's say, an earthquake here, the time it takes to arrive from, let's say, the hypocenter to this receiver here, given the velocity, you can calculate by solving the eikonal equation. And it will give you the first arrival travel time. We have a boundary condition here, which is the travel time at the source is equal to 0, of course, right? And it can give you travel times from source to receiver points in your domain. And you can have multiple receiver points denoted by X here. Now, instead of solving this eikonal equation, what we prefer to solve is what is called the factored eikonal equation. So in the factored eikonal equation, we divide or factor eikonal equation into two parts. So one is called this, which is denoted here by capital T sub 0, is the known factor, and the other is the unknown factor tau, which becomes now a scaling factor, right? And then when you plug this into the original eikonal equation, you get a slightly more complicated equation, but a lot of the terms here are already known because you know capital T0 analytically. So T0 is calculated analytically, and its spatial derivative. So the unknown is this tau. And why do we do that is because the eikonal equation that we saw in the previous slide has a well-known point singularity at the source location. And it is often much easier for neural networks to learn a function which does not contain a singularity. So something like this, what we show here on the right is the motivation here. So if you have, let's say this T, which is this kind of field with source here, and there is a point singularity here at the source location. Now T0 is the solution to, you can think of it as a homogeneous medium with the velocity taken at the source point. And therefore this is your T0, and the scaling factor that is left now is pretty smooth function, at least in the source neighborhood. And therefore, which is much easier for neural networks to, let's say, approximate compared to this. So that's the motivation here of using the factored eikonal equation. So from now on, our unknown is only this guy, tau. T0 is a given for us, and you can take velocity at the source location, and you can just use an analytical formula to calculate T0. All right, so what is the idea? How can we solve the eikonal equation or any PDE basically using a neural network? The idea here is actually we are using a property of neural networks which comes from the universal approximation theorem, which says that neural network with a single layer can approximate any bounded continuous functions, a single hidden layer, I mean. And therefore what we are trying to do here is we are hoping that we could design a neural network that could learn the mapping from the input coordinates X and Z. So we give our neural networks these coordinates X and Z, and it could tell us what is the travel time factor at that point, right? Because T0 is known, we are only focusing on the travel time factor tau. So therefore, this is what we are trying to do here, that we're hoping that this neural network will be like an approximator for the underlying function that we have here. And therefore, what you need here is the eikonal equation itself to do that, and that is, and the training is based on the loss function. So for those of you who have already used, let's say, neural networks in the supervised learning sense, what you do is you calculate loss based on some given labels, right? Here, there are no labels. It's not a supervised learning approach. What you have instead is your PDE, right? So your PDE is going to form the loss function, and that is going to guide the training of the neural network. So the loss function actually is given here. There are two terms. One is the eikonal residual. So we want to minimize the residual, right? So instead of solving the equation, what we're trying to do is trying to find tau that when we plug into the equation minimizes the residual, right? And the boundary condition we have here. So L is our residual, as I mentioned, this is the case here. But to calculate the residual, you need to calculate derivatives of your output with respect to the input, right? And for that, we need to use automatic differentiation. And automatic differentiation allows to calculate derivatives of tau with respect to x. So now you can think of solving any other equation, any other PDE, for example, like a wave equation where you would have, I don't know, pressure field or displacement that you would then differentiate with respect to the inputs a couple of times. And based on that, you could form the loss function, calculate the loss function, and start the training process. The final solution, hopefully it converges, or let's say hopefully the training phenomena or the training process goes smoothly. The final solution is given after multiplying it with your known factor T0, right? So this is your estimate T. So let's think about this in terms of the entire workflow here and just try to understand what's going on here and how to really do this in practice. Okay, so let's imagine you have this randomly initialized neural network. You have a domain, let's say in 2D, maybe one by 1 kilometer square domain, let's say. You have points within this domain. And what you do is, first of all, you feed to your randomly initialized neural network, let's say points selected from your domain, right? So you select some points from your domain, you feed it to your randomly initialized neural network, it will give you some travel time factor, right? And those travel time factors will be total garbage because your network was not trained to perform this task yet, right? So in comes the optimization process, and then you calculate the loss function, this J here, with respect, and you minimize it with respect to network parameters. It needs, to calculate the loss function, you need certain inputs, which were part of the PDE actually, which is this known factor T0, also at those, let's say, collocation or training points, and and its derivative, and also the velocity at those points, right? We're considering right now only the forward problem where we are assuming we know the velocity. Now, what it will do is it will calculate the loss for you, and it will say, okay, the loss is too high. Let's try to go back and update the weights, right? So it goes back, tries to tune the network weights, which are the connections, right? The weights of those connections, comes back, calculates the loss again, and keeps doing this back and forth until you cannot further, reduce this loss function. At that point, you would say that my, let's say, network is being trained, and I'm going to evaluate it on a regular grid X and Z. So now you can evaluate it on a regular grid, these travel times, and multiply them with your T0, and then you have your travel time approximation using the physics-informed neural networks. Now, what about adding more physics into the scheme, right? So one of the things is, let's say, talk about anisotropy. So if you want to add anisotropy, you have more additional parameters. The additional anisotropy parameters, so you represent them with the CIJs, or with these velocities like horizontal velocity, analepticity parameter, vertical velocity, and so on and so forth. So this is for the TTI case here. So you need additional parameters, right? Which again, in the modeling scheme, you would assume that you know. But the only thing that changes actually from the isotropic solver is this guy. Everything stays the same. You only need to update the loss function now based on your new PDE. So what took me more than 2 years during my PhD and a few sleepless nights is a matter of just 2 lines of code here. And things are pretty straightforward here, in terms of adding physics. So that's really a huge gain in capabilities using physics-informed neural networks, because now you can add more physics, and you can just keep updating this loss function here. So let me give you some examples or some tests that we have done, and these come from several publications which are under review, and some of them have been submitted to the EAG annual meeting. All right, so let's start with a simple isotropic model with a linearly increasing velocity model. Now, what I'm going to do is I'm going to consider a source here in the center of the model, and I'm going to try to see whether I could train a neural network to really do or compute the travel times in this case. So here on the left, what you see is travel time errors using the physics-informed neural network method. On right is the fast sweeping method. So it's one of the, let's say, popular conventional method, fast sweeping. And what you see here is these errors are, 10 to the power minus 5. It's much, much lower than what you see on the right, because on the right, it's based on the grid spacing. And I've used the same grid spacing here on both left and right. But you can see at least PINNs can compute travel times accurately, right? So at least we have one thing now off our checklist. What else can it do now? Let's think about transfer learning. Can we, having solved one problem, can we transfer that information into a new problem? Okay, so we were thinking about the isotropic model. Now we're going to add an anisotropy. So what I've done here is I've moved the source really to the top left. I've added a horizontal gradient here in the model, and I've also added anisotropy parameters. And instead of now starting from scratch, which means instead of starting with a randomly initialized neural network, I'm going to take the neural network that was trained for the previous isotropic example, right? And see whether it helps us solve the problem faster. And here are the travel time errors on the left for the physics-informed neural network, on the right for the fast sweeping method. Again, the accuracy is much better than fast sweeping method, given the grids are the same and so on. However, the most interesting plot here is this one here. So what you see here on horizontal axis is the number of epochs or training epochs, or the number of times it has to go back and forth to do the training. And on the y-axis is the loss, and this is a semi-log plot. Here, the two curves that you see here, one is training for this anisotropic model with a randomly initialized model. So if you were to start with a randomly initialized model, you could see it will take a while for you to converge to the minimum, or to converge to the correct solution. Whereas even though we made a lot of changes in terms of source location and velocity model, added an anisotropy, it converges much faster, as you can see here. And we could save a lot of computational time by using this concept of transfer learning. Okay, so we've just discussed a couple of things. What are the other advantages of this framework? And this is something what we call surrogate modeling, right? So previously I was using only X and Z, or the coordinates of my domain, as inputs. I could also add source locations as input, right? And I could train my network over multiple sources. And then when I have a new source, hopefully it will give me a solution instantaneously without having to train the method again, right? So what you saw here was a bit of training was required still, right? And it takes time. Can we get rid of this training? Okay, so that's the idea here, that we're trying to come up with a neural network that can approximate this function X, Z, but also learn the mapping between the source location and the travel time factor field. Okay, so in this case, what I do here is that I take, let's say, 16 equispaced sources in the domain. You could do it randomly, but just for, let's say, illustration, I'm taking here equispaced sources, and I'm going to train my model first on let's say, for not only for the X and Z, which are the domain, let's say, grid points, but also for these source locations. And then when I have a new source location, I'm not going to train anymore, and I'm going to see whether my neural network can give me travel time solution for a new source, maybe somewhere here, somewhere here. And this is very important for, let's say, if you're talking about microseismic source localization, where you have to compute, do such computations thousands of times. If you could train a model that could give you these travel times instantaneously, that saves a lot of cost. Same for seismic imaging, for example, where we need to compute these solutions for thousands of candidate sources. Okay, so that's what I do, that's the train. And for a randomly selected source, I calculate the error here using my newly trained model, which does not require any further training. Now you put in a source location, it spits out the travel time field for it. And you can see it's still, without any training, computation, let's say, computer accuracy is much better than the fast sweeping method. And this is a big, let's say, advantage of using PINNs here, because now for whatever number of sources you have in this domain, hopefully, it will give you accurate solutions. And this is the direction which we push for in terms of building surrogate model for the forward modeling problem, because training takes a lot of time. So if you're solving for a single source or a couple of sources, it's much less efficient than conventional methods. But once you build a surrogate model, it's way faster. So just for comparison, it takes about, I think, 1.5 minutes to train this model. And then after that, it takes 10 seconds to evaluate for a new source. Whereas, if you're doing this, it takes about, I don't know, 20 or 30 seconds for each source. So if you are kind of doing it for a large model with a lot of sources, this is the way to go.
Umair,
What else can
Umair,
we do
can
with this?
can I
Sure, sure, Mike.
can I ask a quick question? Just so you know that you're getting across on Zoom. But I noticed there's a lot of structure in these residual surfaces or these error surfaces. Is that, I mean, I know with ray tracing you get funny effects, and is the structure, I'm just kind of surprised that the machine learning leaves this kind of structure.
Yeah, that's a very good question, Mike. And this is based on the training points that you have selected. So for example, here, if you see, you see a lot of structure, and probably this would have,
Yeah.
you would have noticed this in the PINN error. And this is also because of the function you're trying to approximate and how well you approximate it. So in this case, this is an isotropic case. And in this case, I don't have, let's say, T0, which accurately approximates the homogeneous case. So even in the homogeneous case, I cannot calculate that analytically. So and therefore, I have a function which is very complicated, and it kind of let's say approximates it to a certain accuracy, and that's why you still see some structure coming here.
Okay. Thank you.
Thank you, Mike, for the question.
So the travel time errors that you're showing are not relative to an analytic solution, but to a very fine grid numerical solution, or what?
Exactly. Yeah.
Okay,
because
so the grid artifacts can be preserved when you calculate the error.
True. Yeah.
Okay, and I was going to ask a question. Can you build in reciprocity into the neural network, or does that happen automatically, or
Automatically? Yeah.
because of the structure of the network?
So yeah, you're talking about now you have, let's say, a receiver for which you want to calculate travel time to other positions, right? Is that?
Yeah, I mean, does the neural network know about reciprocity?
Yes.
That it can switch XS and X? Right.
So so you can think of XS and X and Z as, just let's say this is this is one point and this is the other point. So it's trying to give you travel time from this point to this point, and you can then reverse it and do the same, right? Where you have now instead of XS ZS, you have XR ZR, and you have some other point.
Okay, so you can teach it reciprocity, but it's not built into the structure of the layers or anything.
I think it learns it. Yeah.
Okay.
Thank you for very good questions. I'm happy to take questions, as I go along. I think that's better way to let's say explain things. Okay, so what else can you do now? One of the problem is, for example, for land seismic method is you have a lot of topography, and then you have to, if you're using finite difference method, they have a lot of errors, and you might have to design either mathematically flatten the topography, or by using some curvilinear coordinates, or use some more complicated methods like let's say spectral element method, for example. But here, one of the good things is that this is a mesh-free method. So as I told you previously about those X stars, Z stars, those are actually randomly taken from the domain. So now what you could do is you could take these X stars, Z stars from all the points below your topography, whatever you have, and then evaluate your network only for points that are below topography. And then eventually you will get the solution for all the points below topography. So there's nothing you have to change here. And this is really a natural way to include topography, which is pretty straightforward. So here's an example for the BPTTI model. Here is the source over here. And I'm trying to, again, compare with the fast sweeping method. This is the error for the physics-informed neural network. And here is the fast sweeping method. So one interesting thing that you note here is these streaks of errors. And one thing that we have noticed is that physics-informed neural networks, one of the challenges currently is approximating travel times for highly complex velocity fields in which the velocity is changing sharply, because you add a lot more, let's say, high frequency features to your solution. And these networks have what is called a spectral bias. And therefore they learn global features first, and they take a lot of time to learn those let's say localized features. And therefore that is something which even the PINN community is working on, and it's there is ongoing research on that problem. Now, all of what I had showed you before were problems that were already solved using fast sweeping method. As you could see that, we gained some advantage in terms of computational efficiency by building surrogate models. But here is a problem which is even more interesting, because this points to some of the limitations of the current methods right now. So the conventional methods, they break down for certain forms of PDEs, right? And one of those PDEs is this SV, let's say the eikonal equation for SV wave in an anisotropic media. Because you have these triplications and rays passing each other, you have this nonlinearity, emanating from the source, and therefore people who use ray tracing, they use weak anisotropy approximation to avoid such problems. But with PINNs, now you don't have to worry about that, and you don't have to use any weak anisotropy approximation. Here's one example very quickly. So you have this VTI model based on the Greenhorn shale sample, and what you see in the background is a wave field snapshot at, I think, 0.5 seconds or so on, emanating from the source, and overlaid is the travel time solution. Of course, the travel time solution will give you only one travel time, not multiple travel times at each time's, let's say, snapshot. But however, if you see here in the vicinity of this triplication point, PINNs is able to approximate the solution very accurately. And therefore, that's kind of arriving at new possibilities or achieving things that were not possible before. And we have other examples based on the attenuating VTI eikonal model, eikonal solver, in which you have a couple system equations, which is impossible, or let's say currently impossible, to solve with conventional methods. And that is also something we have solved. So, just to make sure I'm on time, I'm not going to talk about that, but this is where we are heading in terms of solving PDEs that were not, let's say, solvable using current methods. So just a quick summary here for the modeling part, and then I'll quickly go over the travel time tomography part real quick. So we have demonstrated the use of neural networks to solve various forms of the eikonal equation. The good thing is that the method is mesh-free and can be used to solve PDEs using randomly selected points in the computational domain. So your source and receivers can be anywhere in the domain. They do not have to be on a grid point as required by finite difference method. They can handle topography very easily. More complicated eikonal equation is just a matter of updating the loss function here. It's not like it takes years of development, really, like the previous schemes. Significant speedup is possible by combining transfer learning and surrogate modeling. So once you have built a surrogate model, it's good for a given velocity model, right? But then you have a new velocity model. Now you can combine transfer learning. So instead of starting from scratch, you could start with a previously trained surrogate model. For this new velocity model, as I showed you, you could train it really fast. But once you have trained for a surrogate model, for all the sources within that velocity model, you could compute it instantaneously. It's like learning a highly nonlinear function, really, analytical function. And easy deployment of computation. So that's one of the advantage, right? Where it's based on TensorFlow. So you could use it on CPUs, GPUs, desktop clusters, doesn't matter. The code stays the same. There are a few challenges pertaining to sharp heterogeneities in the model, which I just mentioned, that which induce high frequency features into your solution. And this is something that these networks are very slow to learn. So this is an ongoing research topic. The other is hyperparameter selection, which is true, of course, for all neural network, let's say, models. That how do you tune parameters? How do you select those parameters? Multi-value travel times is also a challenge, and a pretty interesting one, because now you can compute one travel time, but how do you compute travel time corresponding to, for example, the maximum energy arrival and so on. So regarding the eikonal solver, I have my code here on the GitHub repository with this link here. So feel free to go over to GitHub and take a look at the scripts there and reproduce some of the results I've shown here. We also have some work going on in terms of solving wave equations using physics-informed neural network. This is one of the articles that came out recently in GJI. And therefore, the idea is very much the same. Rather, you have a new PDE, and there are other challenges, of course. So what we do here is we solve the Helmholtz equation, and that kind of gets us rid of all these, let's say, solutions for different time values. Moving quickly on to the travel time tomography part, right? So now we have looked at the modeling part. What about inversion? If you want to get to the velocity model if we have an unknown velocity model. So travel time tomography is used to image Earth's interior from global to local scale. It's been a preeminent technology for many decades. To do that in seismic imaging, it's used to obtain near surface velocity model for subsequent depth migration, or FWI. Also, this is particularly true for surface acquisition, and tomography also finds application in the cross-hole setting, and not only in oil and gas, but mineral exploration, tunnel detection, time-lapse studies for CO2 capture and sequestration, etc. And there are some limitations of the conventional methods, whether they're ray-based or adjoint state methods, is that they use some sort of smoothing regularizers to overcome, let's say, the ill-posedness of the problem, which these regularizers are typically physics agnostic, right? They're not based on the physics of wave propagation. This is one of the challenge or one of the problems, and they end up, because of that, they end up, let's say, compromising the resolution of your solution, because you have to use these smoothing regularizers. They also need an initial velocity model with some given depth gradient for the rays to come back up. And that initial choice may sometimes affect the final solution. So that's another challenge. And again, difficulty in dealing with models having irregular topography. So you need to develop additional tools to do that. So what we do here is, using travel times observed at seismic stations, whether on the surface or in boreholes, we train neural network to approximate not only the travel time factor now, but also the velocity field subject to the physics-informed regularizer formed by the factored eikonal equation. So let's see, what are we trying to do here? We have now two networks, not just one network. So these two networks, one will try to approximate the travel time factor with 4 inputs, coordinates, or you can think of it as receiver coordinates, and these are source coordinates. And the velocity, of course, is independent of the source position. And we are trying to train these two networks, and hopefully once it converges, we have the velocity given by this network. So how can we do that? Is by a combined loss function. So we have now a loss function that guides the training for both of these neural networks. And what goes into this loss function is, of course, now you have data on your receivers. So you want to reduce the mismatch in the data over all your sources, which is this first term here, right? Based on the solution that it gives you, you want to now make sure that this solution is consistent with the data provided, the boundary condition for, of course, all the different sources, and the eikonal residual still stays there. And for the eikonal residual, you need to have the velocity. Now, this velocity is also simultaneously getting updated, and therefore we solve this problem together, this travel time factor and velocity network problem. And this loss function actually is one loss function that we need to guide the whole process. And for those of you who are familiar with FWI, who use a wave field reconstruction inversion, this is very similar approach to that, right? This is a natural way of doing WRI. Okay, some numerical tests that really, this was the work we just concluded, or let's say we just started a couple of weeks back and submitted to the SCG annual meeting. Okay, so this is an example for cross-hole tomography. So we have a model with 100 by 100 or 101 by 101 to be exact number of grids. We have 11 sources here on the left boundary with 100 meter spacing, 51 receivers on this boundary. And what we are going to do is we are going to solve the problem that I outlined, trying to come up with the travel time factor and velocity. And here is the results. So on the left is the true velocity model. This was the initial velocity model. So we don't get to choose the initial velocity model. It comes as a consequence of the initialization of your neural network. And what we have found is the final solution is largely independent of the initial velocity model. And here is the inverted solution, which seems to very well, let's say, replicate the long wavelength features, which is expected of tomography. And it takes only 6 minutes on NVIDIA P100 GPU. And based on my past experience with the adjoint state method, this is way faster than if you were using the adjoint state method, for example. Just a couple of velocity profiles here. The initial one here with blue, red is the inverted one, kind of follows the trend here. That's what it's supposed to do, because you're not solving for all these little bumps. You can use this model now with FWI now, and that helps FWI avoid cycle skipping. And that's the idea here. There's a couple of travel time fits. Black is the observed travel time fit at for for a couple of sources here. As you can see here towards the edge of the model, we have some errors due to elimination issues. The other example I have is for surface tomography. This is the true velocity model. And of course, both of these are synthetic studies that, of course, this is pretty new work. So we will move on to the real data, but it's not included today. This is the model discretization, 51 sources on the surface, 126 receivers. And here are the results. So true model here with this big bump here. And this is the initial model. And it kind of approximates that bump to a certain degree. And this is what is expected of the tomography method. It takes about 20 minutes to do the whole process on a P100 GPU. Just a couple of travel time profiles for two different sources. Here is one for SX equal 2 kilometers. As you can see towards the edge, there are some travel time errors. And here's the other one towards the other edge. Just to conclude, since I'm running out of time, so I've demonstrated the use of neural networks in the second part for the travel time tomography problem. We approximate not only the travel time factor now, but the velocity field as well using neural networks. So the idea is one loss function that kind of dictates or guides your training for both the networks. And one good thing here is that this residual term that we saw comes from the PD, actually acts as a physics-informed regularizer. So therefore, if you have a very ill-posed problem, it's not using some sort of physics agnostic or some smoothing regularizer. Rather, that information is coming from the physics of wave propagation because there is a residual embedded in the loss function. The approach is well suited also to study temporal variations in near surface using surface seismic tomography or larger depths using crosshole tomography. So think of maybe you're monitoring, CO2 sequestration operation, and maybe you have trained a model, done tomography, and then once you have new data, maybe after a few months, what you need to do is you need to use the concept of transfer learning. So you don't need to train all the way from scratch because you already have a model that is close to what it should be, and therefore this neural network can quickly give you a solution, maybe in real time as well. All right, so I would like to acknowledge my contributors, and there are many all over the globe. I would especially like to thank Hassan. Actually, this work started with the collaboration with Hassan, and it started because of our collaboration with MIT, and we were attending a talk by Hassan, and then we kind of talked and brought that idea into our work in geophysics. With that, I'd like to thank you all for bearing me for this much of time, and really appreciate your attention. If you want to look at some of the other work I've done that I just explained briefly, you could look me up on YouTube, and you will find several videos that I keep uploading from time to time explaining these methods in detail. So most of them are related to deep learning methods. Thank you all for your attention. I'm happy to answer questions that you may have.
Thank you, Umair. That was very nice, very nicely presented, and very interesting work. I'm not sure the procedure that you use, Yilong and Adrian, for asking questions. Do people just unmute themselves and ask?
Yeah, you just jump in, unmute and unmute yourself and jump in.
Okay.
So I have a question, Bill Rody.
Sure.
The physics informed comes through the loss function,
Exactly.
building loss for not obeying the physics basically into the loss function.
Right, yep.
And so what seems to make it different from just a data-driven neural network is you have to perturb. It involved derivatives with respect to the inputs. So does that change the training procedure? Like you're having to perturb the inputs just to be able to calculate the loss function, or how does that work?
Yeah. So this is taken, and this is one of the really reasons why this is taken off, is because of the ease to do this procedure, where you do it simply through the procedure called automatic differentiation, which is an algorithm to compute the derivatives. So you can think of it as it's not symbolic differentiation, nor it is some kind of finite difference method, but it is a way to, it's based on the chain rule idea.
Oh,
so
it's back propagation.
Right, exactly, yeah.
Yeah. So a related question then is, when you do the tomography, you're combining two loss functions, one that penalizes you for not obeying eikonal and the other for not fitting the data. There must be some weight between the two, and is there, and if so, is that a problematical on how to choose that weight?
Right, that's a very important question. And so far as you've seen that the examples I've worked on are synthetic examples. So, once you have data with noise coming in, probably you would want to do the tuning part. And this is a question that needs to be answered, of course. How easy or difficult it will be, it remains to be seen. So far we haven't done any tuning of weights here. It's based on just the loss function that you see here. And it's trying to minimize both the factors.
And the combined loss, it wasn't a big deal whether you need to put a scale factor in front of one or the other?
So it may happen that, one of your term may dominate the training procedure, right? Because of one reason or the other. So it's also possible to have a gradient scaling where, once you are, right? Yeah.
Yeah, so that it sort of automatically balances it.
Right, exactly, yeah. So you could automatically do that, and the user does not have to take care of this procedure.
Somehow showing these two networks like this seems a bit reminiscent of adversarial networks. Is there any way to think of this as some kind of a GAN approach, or is that?
So in GAN, I think the two networks that you have opposite goals, right? I think in this case, both networks have the same goal.
So they're working together, I guess, in this case, as opposed to trying to outsmart each other.
Yeah.
I have a question. Can you hear me?
Yes. I do.
Okay. Thank you for this nice presentation. I'm curious. Do you experience some so-called gradient vanishing problem when you train the network? And if so, how do you overcome that? And this is my first question. The second question, so when I look at your input, which are few inputs, this reminds me the complex valued differentiation, which allows you to not do back propagations. So which means when you put the input, you can get the tau, the travel time, and the gradient directly without back propagation. I don't know if this is a valid option.
I'm sorry, Wei, I did not catch your second question. Could you please elaborate it a little bit more?
So
there's a lot of noise here.
Yeah, sorry, I'm in a room. This reminds me the complex valued gradient technique. Basically, it allows you to compute the gradient without back propagation. So essentially, you make your input as a complex numbers, and at the output, which is the tau here, you have your gradient from your complex component. So the benefit is that you do not need to do a back propagation but you still get the gradient. So I don't know if this is a valid option to reduce the computational cost.
Okay, so regarding this point, Wei, I'm not familiar with this method that you're mentioning, so I need to look at it first and then maybe give you a better answer to this. Regarding your first question, the gradient vanishing problem, so we did not experience any of that with this network. I haven't explored it, why we did not experience this, but probably the network, these are just, fully connected neural networks, and typically you have these gradient vanishing problem for more complex forms of the neural network.
Okay, thank you very much.
Hello, I have a question.
Yes, Zilong.
So when you compare the PINN with the fast sweeping method, I'm not sure. Do you for both methods, do you use the same mesh grid or?
I compare with the fast sweeping method because that is one of the most popular method, or probably the most popular method for computing solving the eikonal equation. That's the reason. And yes, I use the same mesh actually. So that's you need a regular grid to solve the eikonal the fast sweeping method, right? So in both cases, I use the same grid. But actually, for pins, I don't use all the grid points. I train on only a small collection of grid points randomly selected, typically 20 to 30%. And it's because the more training points you use, the let's say the more training cost it will be in terms of time. And it depends on the heterogeneity of your velocity model. So if your velocity model is highly heterogeneous, you would need a lot more, let's say, training points. But if it's something very smooth and simple, then you don't need a lot of training points.
So the following is that, so basically you randomly select like 20 to 30% of the grid, and then you train the network. And the image you show is that you use the trained network on all the grid points, right?
Right.
And do you have a comment on the computational time for training the neural network compared to the fast sweeping method? Because from my understanding is that if you just using the basic toolbox.
Mike, do you hear Zilong? I don't know.
He cut out.
Okay.
Yeah, I heard about a third of his question. Zilong?
Can you hear me? Can you hear me?
Now we hear
Yes,
you.
yes,
we
we do
missed
now.
some of your question.
So is it okay right now?
Yes.
So my second question is that can you give a comment about the computational time for the PIN and the fast sweeping method comparison? Because from my understanding that if you use a toolbox like TensorFlow or PyTouch, when you're doing the training, you only use that first order method to do optimization. So I'm not sure whether it will be very fast compared to like you direct solving the PD.
Okay, very, very good question. So one thing you could do also is you could go over to GitHub and try some of these yourself. But I can point out to this example here, for example, the surrogate modeling one. So it took us about, let's say I told you, about 1.5 minutes or so to train the surrogate model. So you don't have to use just this first order optimizer like Atom. If you feel you could also use LBFGS, and that's what we do in some of the examples that I showed once you are close to the solution. But for LBFGS, you have to use the entire, so you cannot use mini batch technique for LBFGS, right? So if you have a big problem, that is a restriction that you have with LBFGS, and you have to use Atom to do the mini batches. But here, I use about it takes about 1 minute and 30 seconds or so to train the surrogate model. And then any evaluation after that takes about 10 seconds. Now, compared to fast sweeping, so I did this in the paper, and I remember that it takes about, I think, 80 source evaluations. So for the first 80 sources, the compute time is the same for PINNs and FSM. So PINNs is catching up, and it's kind of there for the first 80 sources, but then for the rest, it's, I don't know, 10 or 12 times faster than fast sweeping. And of course, these are, let's say, rudimentary analysis, because then you have to properly tune the fast sweeping method to do this analysis. But I'm just giving you some numbers, which are really very basic numbers. But yeah, you could do something really fast here with PINNs.
So for the fast sweeping, do you also use the GPU to accelerate it?
No. So that's, you can think of it as an advantage, whether you run PINN on CPU, GPU, you don't have to change the code, right? Whereas for fast sweeping, you have to rewrite the code.
Yeah. Thank you.
Thank you, Zilong.
Hey, Umar, can I ask a real quick question here?
Sure.
Yeah, so you mentioned that one of the advantages of PIN-based tomography is that it doesn't require this arbitrary regularization, right? But notice that the velocity model you obtain from PIN-based tomography is typically smooth.
Right.
Looks to me that the PIN network does it naturally prefer smooth models? What's going on here?
Okay, so that's because of the inherent limitation of tomography. So if you're working with travel times, using any other method, you would get something that only follows the trend. It does not give you these local variation. That's the inherent limitation with travel time tomography.
Yeah, that makes sense. But I'm just wondering, I mean, for conventional method, we can manipulate the regularizer to make it blocky, right? We can use sparse norms. So I'm just wondering which part of your network or your loss function that give you this, that is responsible for the smoothness that we observe in your velocity model.
So that is something, that's part of the network that I mentioned. Is something called a spectral bias. It prefers to learn first the smooth features and then the high frequency features. So, but what you mentioned, Jaja, is that you could also add other regularization terms here in the loss function if you want some sort of blockiness or whatever. But also what you could do is you could, in addition to just having X and Z as inputs, some people are looking into using Fourier features, which kind of give you these let's say sharper features into your solution. So that's something I haven't done, and it's just very preliminary tests, so I don't prefer to talk about that yet, but there are possibilities. But also, if you want, you could, like any other optimization method, add a loss function here, a fourth one.
Thank you very much.
I have a related question.
Mm-hmm.
You had said, I'm not sure I understand what you said. You said that the loss term for the eikonal loss acts as a regularization, but it seems like the ill-posedness of the problem exists even when you have that loss to zero. So there must be some other kind of regularization going on. You didn't have a third term with smoothness. I mean, could it be that the way you're regularizing is the parameterization of this second neural network? How many layers, how many connections?
Mm-hmm.
And it's that network parameterization that's actually doing the smoothing and the regularization.
That is possible. So I haven't talked about what kind of network I use. Typically, the travel time factor network is much larger than the velocity network. So the velocity network is much smaller because of the function that's trying to learn is simpler compared to what you see here. So I'm not sure about this thing about where this smoothness is coming from. I think in my opinion it's part of the problem. So it needs to be seen with other regularization terms, how things change, and with other, let's say, network configurations, as you mentioned.
Well, there's parameterization and regularization, but even if you built in the eikonal equation as a constraint rather than as a penalty term, the problem's still ill-posed. There's places where ray paths don't go.
Right.
So my gut feeling is it's the way you built the network that sort of guarantees some smoothing, or the number of iterations you do on the training or something that's sort of indirectly doing some kind of smoothing.
Okay, I need to think about that more. Thank you for your comment. Right now, I don't seem to have a clear picture about this thing.
I have a comment. I have a comment for that. So
sure.
Can you mention how many iterations you have for your tomography work?
Sorry, Zilong.
Because I in our group we used to look at some paper that to discuss how neural networks work. So basically, the paper tells you that at the very beginning of at the beginning, it will try to recover the low frequency component of the function. For example, here is that it will try to recover the low frequency of the function from X to V. So if you have very limited number of iterations, then you can expect some like low frequency smooth result.
Yeah, thank you, Zilong. Yes, you're right that this is the spectral bias of neural networks, that they learn smooth features first, that I mentioned at a couple of points. In this case, what I do is first I use the Atom optimizer for a certain number of iterations, say 100 or 200, and then I switch to LBFGS until it converges, so until it stops improving. That is the point where it stops. So I don't, ask it to stop at a certain number of iteration.
Are there any other questions? It's been good discussion.
I have a small question. Thanks, Umair. Very nice talk. Small question is related to comparison with FSM. Do you compare with factored FSM or with standard one?
No, in this case, without the factor, just the regular fast sweeping method. All the comparison is based on the regular one. Yeah.
So it means like the misfits when compared to factored would be more or less the same, because factored is about 10 times more accurate.
Right. Yeah. So if you use factored for the let's say the FSM, then it becomes computationally more expensive for the FSM part. But yeah, of course, the accuracy increases. And yes, you could also use high order methods. In this case, the idea is here that if you want to have similar accuracy, what is the computational time that you need for FSM? So that's why I used a regular one to compare here and see what is the difference.
It's just that in PINN you use factored equation, and FSM you use the standard equation. So it makes probably more sense to compare the factored FSM, but of course there will be an advantage then of PINNs in terms of computation time. So because
yes, the advantage would become more highlighted, let's say. Yeah, so there was no particular reason, but also, Dennis, there are many high order methods which, in this case, with PINNs, you cannot construct a high order method. It's just the same accuracy, right?
Yeah, right. Okay, thanks.
Thank you, Dennis.
Any other questions? Well, Umair, thank you very much. Appreciate your willingness to do this, particularly at a late in the afternoon or late in the early evening your time on a Friday. Appreciate your flexibility on the timing. It is nice that with the availability of Zoom that we can actually have seminars by people who don't have to travel all the way to Boston for that.
Exactly.
Although we look forward to seeing you maybe this fall before SEG in Boston.
Oh yeah, let's see.
Yeah.
I hope so as well. Yeah.
So thank you very much. On behalf of everybody who was involved and asked questions and listened, we enjoyed your seminar a great deal. So thank you.
Thank you, Mike. Yeah, thank you for the invitation. I'm very happy. Yeah, wonderful.
Thank you, Matt.
You.
Bye.
Bye.
Bye.